All right, and so we'll get started for our June 21st ME 316 lecture. We kind of had a surprise holiday last Friday, but it was kind of well timed because on Wednesday, you got to see the blast from the past, and I just posted the lecture video from last summer. Um, and then that kind of finished out the whole topics on torsion. And so that Friday holiday of Juneteenth Day really was well timed because we're just starting beam bending now. And so I'll go ahead and share my screen. And I have the lecture notes posted on D2L for this, and it looks like we have about 15 pages, so it's going to be a little over an hour, I think, today in getting through this lecture. We'll see where we're at about 9:50 time frame and see if we should have a break at all. But chapter 6 just deals with beam bending, where a beam is just a long, slender structural member that often supports perpendicular loads, moments, and axial forces. And so if you're looking at bridges, airplane wings, vehicle frames, traffic lights, sign structures, those things are all beams. It's really neat to look at how Boeing, for example, evaluates the strength of the wing. They'll take a whole plane and just load the end of the wing until failure. Just looking at the maximum forces that can be placed on that. But there's different beam classifications that are located in your textbook. Simply supported beam, a simple beam, has a pin on one end and roller at the other end. An overhanging beam has a pinned at one end, roller, and then it's overhanging past that roller. Cantilevered beam is fixed on one end and free. Fixed really implies that there's no rotations at all at the fixed support, which means there's no slope or rotation, whereas a restrained beam has slight rotations allowed. All three of those are statically determinate. And I've seen those classifications come up in things like a graduate type of course study exam, just to make sure the graduate students know the engineering fundamentals. And so it's come up where just draw what a simply supported beam looks like. And those are all would appear in figure 6.1 in your textbook. I was gonna check to see if I might have those figures to share with you. Let me see. There we go. I'm going to do this as a side by side. And I'll bring it back up here in a second. playing with multiple windows is always interesting. All right. So we'll share the screen again. We're back. All right. And so I was thinking I probably had some figures to go along with this if I mentioned that in the lecture notes. We have the figures that go along now with the beam classification over here on the right-hand side. And so simply supported again is a pinned connection. And again, this can support reaction forces in both the X and the Y direction, whereas a roller support can only support a force in the vertical perpendicular direction. So that's a simply supported beam. An overhang beam is pinned, a roller, and then overhang from there. And then a cantilevered beam is fixed on one end and free on the other one. So it's good to be able to see those figures in relation to the classifications. I noted that earlier in the summer semester here where Hibbler's book just views a roller as providing a vertical force. They don't indicate which direction that vertical force has to be. And so the way Hibbler recognizes this could be a downward force too, like keeping this beam from going up, which would physically make more sense if the roller were then on the other side. Just be aware that that's how Hibbler is representing a roller, that it can provide that in either direction. From a practical standpoint, you would have to determine which side the roller would need to be on for that to happen. Then I have a note on recalling the reactions shown in table 1.1, also shown in table 12.1. And so again, that roller just indicates no displacement in the Y direction for Hibbler. And that force could be in any direction. I'm going to expand this one out so we can actually see those. Oh, I grabbed the wrong thing. And so when we look at reaction forces again on table 1.1, we just see that a cable can only provide an axial force in line with the cable, roller, vertical force, a smooth incline. It would have to be perpendicular to that incline. Journal bearing, just force perpendicular. Pin, again, forces in both directions. An internal pin, forces in both directions. Fixed support can support forces in both directions as well as a moment. And then a thrust bearing is able to support an axial load as well. So that shows up early in your Hibbler textbook. And then as you move along into chapter 12, they show the corresponding displacements at each point of a roller. Displacement 0, same thing with the pin, displacement is 0 for all those cases. And it's only when you get to a fixed support that the slope theta is also 0. So remember again that V here represents the displacement in the Y direction. We're in chapter 6 right now, and so that's kind of why I point out these different tables and figures, because chapter 6, it's talking about beam bending stuff, but you have these concepts back from chapter 1 that they introduced, and then you will have these other concepts in chapter 12 that you haven't even got to yet, which makes it good to kind of make everything clear here. We'll shrink that back down for now. So I think we're good there. And And again, just the note on the roller, just make sure you consider if this is realistic for, say, a design situation that you're doing. If it's just resting on a roller, it couldn't provide a force in the other direction. And so refer to figure 6.1, 6.3, and 6.4. I don't know if I have that here. No. So I'm just, at this point, we're having you refer to those sections in your textbook, 6.1, 6.3, and 6.4, really on looking at the definition of strain for a beam and bending. I might have some pictures that I've drawn. Yeah, so I have pictures that I've drawn on the next page that clarify this. But when you're dealing with a beam and bending, if this is bending down, for example, the bottom half of the beam is going to be stretching out and expanding, whereas the top half of the beam is going to be contracting inward. And so the top side of the beam in this situation will be in compression, and the bottom side will be in tension. It is a strain in the X direction, and that just, again, strain is just the displacement over that original length, and that can be related to the radius of curvature is -1/rho times the Y value, the distance from the neutral axis of the shaft, which would typically be in the center if it's a symmetric cross section. And so bending stress, relating that through Hooke's law, it is a 1D loading condition, so we can relate it through Hooke's law. Sigma x is equal to the Young's modulus times the strain in the X. And if we make that substitution in for strain in the X, we end up with -E/rho times Y. And this is where we then get into that definitions. And I'm going to see if I can move this a little bit over so we get to see everything. But main thing in dealing with beam stresses and deflections, we do have to remember our positive definitions. And so when we make a cut, positive shear is going down on this left side figure, and counterclockwise moment, P, the axial load, always goes outward from the cut, and the moment and shear are just equal opposite from the other side. And so this is where we're getting to that discussion on if we have an internal moment that's developing due to bending, that beam is going to develop a radius of curvature rho. And we can identify then what the strain in the beam is and the stress is based on that radius of curvature that develops. Y, if we look at the beam, is just that vertical direction from the neutral axis. In this case, say we're dealing with a rectangular beam, the neutral axis would be in the center, and Y would just be vertically upward. And so if we look at that, again, the strain is going to be a function of Y, the stress is going to be a function of Y, and that's why we call this the neutral axis there in the center, because that develops a linear relationship but for the stress and strain as a function of position, and the stress and strain are zero at that neutral axis. There's a location in the middle of the beam that does not experience any stress. But as you go up in a positive Y fashion, that is going to be in compression on the top side. And then when you go down in the negative Y direction, that'll be in tension. And we see that with the relationship as well, with the minus sign being in front there. So if you go positive Y, you'll be in compression. The negative sign is shown, same here. When you go down in the negative Y, then two negatives turn that into a positive, so that'll be in tension as you go down when you're dealing with a positive internal moment. Other things to note is that the positive moment creates a bowl shape, again with compression on the top and tension on the bottom. And so if we look at that, we can really then relate that we'll have a maximum stress on either side. And so we could define that linear relationship for stress as a function of y. And that's just equal to minus y over c, or again, c is the maximum distance from the neutral axis to the outer edge, and times sigma max. And so what this does then is if y is equal to c, where you're on the outer edge, sigma will just be equal to sigma max. And if you're at the other end, a minus c, that would be a positive value then for your sigma equal to sigma max. If y is equal to 0, that tells you the stress is equal to 0. And so we really need to know what this stress is as a function of y so that we can integrate it and find a relationship between the internal moment that's being applied and the stress that's being produced. And so that's what we're doing here over the next few areas, is we're just summing forces now in the x direction equal to 0 for equilibrium to be satisfied. And so it's just really an integral over the area of sigma times the dA. And so we can substitute sigma in for this, minus y over c times sigma max, derivative with respect to the area. Sigma max is a constant, c is a constant, so those can be pulled out with the minus sign, and we're left with the integral of over the area of y dA. And so for this to be equal to 0, since both these are constants, that tells you that the integral over the area of y dA has to be equal to 0, which is the thing that really forces that neutral axis at the centroid of the area. And so then if you sum moments, you'll find that your sum of moments then is minus sigma max over c integral over the area of a y squared dA. Essentially your force times your distance gives you your moments. And this term, the integral over the area of y squared dA, is equal to your area moment of inertia, I. And so if we make that substitution in for I, you can solve for sigma max as a minus mc over I. Moving c up to the numerator here and dividing through by I will give you your expression for sigma max. And again, that's going to be occurring on the top and bottom surfaces. And so C, if you go positive in the y direction, you would put in a positive C value there. And so your stress would be a negative. If you put in a minus C value to get to the bottom, that would turn that around to a positive. I think generally for the way I do this, I tend to just look at MC over I and then look at the problem itself to determine which side is in compression, which side is in tension. But then that same trend follows through that if you wanted to know the stress anywhere through the thickness of the beam, you just replace C with Y. And you could do that by solving for sigma max here and making that substitution in for sigma max, and you would get sigma equal to minus my over I. And so both of these really represent then the correlation between the axial stress that develops as a function of the position through the thickness of the beam based on the bending moment that's applied. And so this is now the correlation to what we had with axial loading equal to P over A. Torsional loading, we had that shear stress is equal to TC over J. Now bending, we have our primary relationship here, where stress is equal to MC over I for that maximum stress. And so these are all relationships that are good just to commit to memory. I think that makes it easy when you're going through calculations, if you are able to remember these things and you don't have to look them up all the time. And so just defining all the variables in there, moment is a unit of force times length. Y again is that distance from the neutral axis. And sigma x is going to be a maximum when y is the furthest from the neutral axis, y equal to c. I is the area moment of inertia, or the second moment of area. And so kind of the same thing that we did last time when we discussed the polar moment of inertia for torsion. We'll just introduce that integral expression. And then as we continue on, we'll dig deeper into that so that we can solve for those relationships as we go through that area integral. But a lot of these things do break down into a nice algebraic form that you're able to do quickly then as you solve your problems. But I is equal to the integral of y squared dA. If we have a rectangular section, which is common, of base B and height h, its area moment of inertia about the z-axis here is bh cubed over 12. And then the same thing for a circular section. The area moment inertia about the z-axis is pi d to the 4th over 64. I'll kind of make a note of this. One of the odd things that happens with your Hibbler textbook and even other textbooks is when you look at like tables in the back of your book, for example, when they classify their beam or draw their beam, they draw it with respect to the x-y axis. And so you end up with your area moment of inertia about the x-x axis and the y-y axis based on the tables. But I think that causes confusion because typically when you're looking at along the length of the beam, this is probably a good figure here on the right to represent that. Your x-axis is usually aligned along the length of the beam. And so when you're solving for your moment, you're going to be solving for that as a function of x. And so when you look at the cross section, that's technically on the YZ plane at that point. And so I've made that distinction here for that case. And so the main thing is just to realize that there's kind of a misrepresentation of placing that in the back of the book as the XY axis, because the X axis is already defined as along the length of the beam. And so it'd really be the YZ plane that we're looking at. And so be careful on that. That shows up in, I think, many textbooks. They just kind of reorientate their frame of reference. That essentially is all they're doing when they calculate those area moments of inertia. Then another thing as well is really just this definition of the base and the height. When we're calculating I of z for this case, we have the base times the height cubed divided by 12. And if you were to look at the area moment of inertia about the y-axis, these would flip around. So it'd be height times base cubed over 12. And that gets confusing for me, trying to keep track of that. I just like remembering simply I is equal to base times height cubed over 12, and then define your base and height based on which axis you're bending about. So for the IZ axis, the area moment of inertia about Z, I would define the base and height as shown here. But if we're solving for I about the Y direction, I would just redefine these. So the base would be this long edge and the height would be the short edge. And then you only have to remember that one expression. And I don't think it causes confusion then keeping track of just which one you're defining there. And so I did make that special note that the tables in the appendices show those on the XY plane instead of the YZ plane. And it's just that they're reorientating things. But I think that has caused confusion in the past. With those tables in the back of the textbook, in addition to the area moment of inertia being defined, they also define an S value, which is the section modulus. And that is extremely useful. When we look at, again, our relationship for our maximum axial stress, we have minus MC over I. And so if we're trying to design a beam to achieve, to not exceed a certain maximum bending stress, we end up with two variables that are a function of the geometry. We have the C value, which is the distance from the neutral axis to the outer edge, and then we have the area moment of inertia. And so that makes it complicated to try to solve and design beams based on adjusting those two parameters. And so the section modulus is defined as just that ratio of I over C. And so you end up with your maximum bending stresses minus M over S. And so then that makes it a little bit easier. If you know your bending moment, you know your maximum stress that's allowed, you can solve for a minimum section modulus that's required to support that. And then based on the table, you can just look at that and essentially go up until you reach a section modulus that is sufficient. It would have to be equal to or greater than what is required to support that load, that bending moment, and maintain stress value less than or equal to what is allowed. And so again, S is useful when designing selecting beams, since I and C are both functions of geometry. And so next up, I believe we are looking at now this figure. But the main thing that we'll find in this situation is that both the internal moment and shear force, those internal values, will vary along the length of the beam. And so what we need to do is determine when these values are maximum in order to calculate the maximum stress based on those bending moment and shearing forces. And so chapter 6 deals entirely with the bending moment and the axial stress that develops with that. And then chapter 7 deals with the transverse shear stress that the transverse shear stress that develops and the shear associated with that. And so chapter 6 here will focus on the bending aspect. But in this process, what we'll do is we'll create shear moment diagrams just to graphically see the variation of both shear and the bending moment along the length of the beam. Those are nice graphical representations, but they're really obtained just by equilibrium, drawing your free body diagrams, looking at developing your shear and your moment as a function of X along the length of the beam. And so I have an example to go through to get us started on that. This is problem 6.6 modified slightly. What we're given is this simply supported beam here with the 800 Newton and 1500 Newton load applied. And AB, that shaft is a 40 millimeter diameter rod. And so what we're asked to find then are the reactions. What is the internal shear and moment for each section as a function of X? And then 3, what is the maximum bending stress? We haven't really looked at the transverse shear stress effects yet, so for this problem, we'll just look at the maximum bending stress. And we really get to utilize all the things that we've learned already from equilibrium, compatibility, constitutive relations, and just starting out with a free body diagram. And we know that these bearings can support forces in the Y direction. And so you have an AY, B of Y. You have your 800 Newton force located 125 millimeters away, another 600 millimeters to 1500 Newton meter force. That is 75 millimeters from that end. And so we really have 3 sections throughout the beam where anytime you have a force, you'll have to do a new cut. Anytime you have like a roller or something, a boundary condition, you would have to do another cut. And so essentially, we'll do this in multiple steps. The first step will be just identifying what the reaction forces are based on this overall free body diagram. And then we'll do individual cuts to see what the internal forces are along the length of the beam. When we go through this process, we do want to define and establish a datum as a definition for X that will keep consistent for all of the free body diagrams. So this case, we'll leave our location A as the datum, or 0 is defined for X, and then it's positive to the right. That's important to maintain that datum relationship for each section of the beam so that X is consistent for all that. And so determining reactions, we have 2 unknowns here. And so remembering back to statics, intro to solid mechanics, if we sum moments about A, that'll be really nice because our force at AY would not have a moment associated with that. So we'll end up with one equation, one unknown to solve for BY. And so summing moments about A counterclockwise positive, we'd have BY times 800 millimeters minus 800 newtons times 125 millimeters minus 1500 newtons times 725 millimeters. And just remembering that again, counterclockwise positive, our force BY would cause that to rotate in a counterclockwise manner. Our 800 Newton force would cause that to rotate in a clockwise manner. And the same with our 1500 Newton force. Essentially just think of this point A being on a pivot. And if that force BY were applied, which way would that rotate? Is all you really have to do. And summing your moments. And that gives you one equation, one unknown, where you can solve for B of Y. I put several significant figures past that so we don't have any round off errors. Then once you have BY, you can sum forces in the Y direction, AY plus BY minus 800 minus 1500 equal to 0, and you can solve for AY. One thing that we are doing in this process is neglecting the weight of the beam. typically the loading that's applied to the beam is much greater than the weight of the beam, so that becomes insignificant. But that may not always be the case, so that's something you should consider based on the loading. Do I need to take the weight of the beam into account? And so for this instance, if we have this 800 millimeter long beam, which is about 0.8 meters, just a little under a meter. If we were to include the weight, we would just draw that on the free body diagram at the center of the beam as the force acting down. And that would just increase our AY and BY values. But that's the first step, is to identify then what your reactions are. And so we've solved for AY and BY now. That was the first step. Now the next step will be determining the internal forces for each section. And so what we'll do is really just imagine a cutting plane going through that section 1, and then we'll draw a free body diagram of this left-hand side, what is remaining. And so we'd have AY going up, and then at the cut, we'd have a V1 acting down and a moment 1 counterclockwise. Again, we're maintaining that positive definition for how we're drawing these, so that we can represent V1 and M1 accurately with respect to the positive convention. For what we're doing here in chapter 6, it does come into play in determining the appropriate sign on stress. If you follow this procedure and you're using the sigma equal to minus MC over I, and you keep track of your sign C, it will come out properly what the sign is for stress on the top and bottom of the beam. Typically, though, you can just look at the physics of the problem and see which side is in compression and which side is in tension. So that's not too much of a struggle from that standpoint. But where this becomes really important on maintaining the positive definition is when we get into chapter 12 and looking at the deflections of beams. We have to have the correct sign on these moments as a function of X, so that we get the displacement to come out properly, the sign on that, so we know if it's deflecting positive upward in the vertical direction or negative downward in that direction. But this is just the free body diagram. We have our reaction force AY on the left, our internal forces and moments that we're trying to solve, and it's a distance X away from AY being our datum. And so with that, all we have to do is sum forces in the Y. We'll have AY minus V1 is equal to 0, which just tells us that V1 is equal to AY. And then if we sum moments about the cut, we don't have to deal with V1. We'll just have our moment 1 minus A1 times X equal to 0. And so we find that M1 is just equal to that reaction AY times the X value, the location where that cut is located. And so what we're seeing is that V1 is a constant throughout that first section, but the internal moment varies linearly with respect to X. What that's really saying is that cut could occur anywhere between where our reaction at A is and where that 800 Newton force is applied. And that gives us a relationship for our moment then as a function of X. And so there's our V1, and M1 is A1X. A1 was solved on the last pages, 815.625 Newtons. So there's our M1. Oh, I did not want to zoom in on that. All right, so then you go on to section 2 and make a cut again. And so for our free body diagram, we just continue to draw things from the far left side, establishing that same datum. And now when we draw our free body diagram, we're now seeing our 800 Newton force. We've passed into this area here, and we have the same thing, internal force V2 and an internal moment M2. This is commonly how I do things, so that we can keep track of our internal moments and shear forces, just defining them in that manner. And this is going to be valid then between 125 millimeters to 725 millimeters. I think I put that up on section 1 too, with that these expressions are only valid from X from 0 to 125 millimeters. So free body diagram, just summing forces on the Y, you'd have AY minus V2 minus 800 is equal to 0, which just tells you that V2 is equal to 15.625 newtons. So again, a constant value. And then summing moments about the cut, you would have M2 minus an A1X plus 800 newtons. That's going to cause a counterclockwise rotation. So plus 800 newtons times X minus 125. And so when we start seeing these forces, you'll see that show up quite a bit, where we're taking the full X value minus 125 to get that distance away from the cut. And so you can solve for your internal moment 2. Rearranging, you'd have A1X minus 800 times X plus 800 times 125. And so collecting all those together, you'd have 15.625X plus 100,000 Newton millimeters for that moment. And then finally, section 3, same thing. On occasion, it is easier, instead of drawing everything from the left-hand side, just to draw the right-hand side of the cut. And so this is a nice little trick that is often beneficial. So I've drawn the right-hand side of the figure where we have BY as the reaction. We'd have a V3 positive up, M3 positive clockwise. And so to do this trick properly, you still have to reference that same datum at A. And so your X distance would be referenced from that same datum to where the cut is. But then we know the full distance from that datum to BY is 800 millimeters. And so we can establish it with this free body diagram, summing forces in the Y. You'd have V3 plus BY is equal to 0, which tells you that V3 is equal to a minus BY, minus 1,484.375 newtons. And summing moments about the cut, counterclockwise positive, that would be summing moments about the cut again. That distance of what's remaining is 800 millimeters minus X. So we'd have counterclockwise moment created by BY. So BY times 800 minus X will give us the moment created by BY. Then minus M3 is equal to 0. And so this little trick of 800 minus X is really how you're establishing X properly in that relationship. And you can solve then for M3 as a function of X. With that, if you were to have drawn the left-hand side free body diagram all the way out to here, you would have had to contend with 2 forces to deal with and summing your moments, which would have made this expression a lot longer, and then it would just collapse down into the same form. And so this was a little bit quicker to do the free body diagram of the right side. And so based on that, we can draw then the shear and moment diagrams And they come directly from these values. We saw that the internal shear was 815.625 newtons as we started off. As we got to the second section, it was 15.625, constant again. And then as we got to that last section, it was minus 148.375, so it drops down. And so what that's telling you is that our shear force is constant through each of those sections. And the other thing that we'll find, we'll start talking about this here down below, is that when you start looking at the relationship between the shear force and the internal moment, it's really looking at the area under the shear diagram. If we take the 815.625 times 125, that'll define our moment, 101,950 Newton millimeters. When there is a linear or a constant relationship for the shear, there'll be a linear relationship for the moment as a function of x. When there's a linear relationship for the shear, there'll be a second order relationship for the moment. This is one thing that you can do easily graphically, developing your shear moment diagrams, just calculating out the areas. And so with that, again, we have the area of this section, 101,950 Newton millimeters. And then if we look at the area of this section, 15.625 times this distance, it'd be 725 minus 125, 600. When you multiply those two numbers and add it to 101,950, you get 111,300. And then when you multiply these two values, minus 1484.375 times that 75 millimeters, that's going to drop you back down to 0. And so the basic relationship then is that your shear force is the derivative of your moment with respect to x. And so if you separate your variables, put dx on the other side and integrate, it shows you that your moment is going to be equal to the integral of the area of the shear, so the area under the curve. And so that's our first relationship. And then the other thing too is you see that with dm dx, if you look at the derivative of the moment diagram, with this being a constant slope, that would give you a constant value for your shear with respect to that. We have another relationship too, in terms of the higher order, looking at a distributed load along the length of the beam. And so dV dx is equal to omega when we go up a higher order. And we'll show all those relationships, how they're all related to one another as we continue on. But with respect to this particular problem here, the main thing that you're capturing from all of this is that the maximum moment is occurring at this 1500 Newton force and is 111,330 Newton millimeters. That we can use to figure out what the maximum bending stress is. And likewise, when we get to chapter 7, we see the maximum shear force. We could use that to find out what the maximum shear stress is for this particular beam. But remember, these are just algebraic relationships too. So if we look at the moment as a function of x, that's what these equations represent. If you were to plot this, M1 815.625 times x, that would plot as this first slope right here. And so everything can be determined from your free body diagrams and your equilibrium expressions that you're comfortable with. But it can often be quicker to do that from a graphical standpoint. And so main comment there, moment represented by the area under the shear diagram. And then now we can move on to figuring out what the maximum stress is, just equal to minus MC over I. I is equal to pi d to the fourth over 64. And we're given a diameter of 40 millimeters. So that gives us area moment of inertia of 125,664 millimeters to the fourth. And so I guess touching back on that area moment of inertia, it's really just an object's resistance to bending. And so as I increases, the deflections that you'll get for the beam will be lower. And likewise, the bending stress will be lower as I increases. And so sigma max, again, is going to occur on the top side. I guess sigma max, it's going to be compression on the top side and then tension on the bottom side. So we'd have to put in a minus 20 for C value. So sigma max is equal to a minus our moment max, 111,330 Newton millimeters. C, if we want the positive stress, that's on the bottom side, so minus 20 millimeters, divided by the I value there, will give us 17.7 megapascals for the maximum bending stress. And again, that C of minus 20 just signifies that the max tensile stress occurs on the bottom of the shaft. And so this is kind of a nice example problem just to develop that concept of the shear and moment diagram. I added this example problem, I can't remember if it was last summer or the time before that I taught, but this was kind of a nice straightforward example. The next example that I show, it gets a little bit more convoluted. And so I thought that was probably not the best example problem to start with on developing these concepts. And so I kind of liked adding this one in, so it was simple and straightforward to see the drawing of the free body diagrams, solving for your moment as a function of X, and not having to deal with difficulties with the next example problem. But I think that's a good pause point. Did you want to take a break, Jordan, or did you want to continue on?
Yeah, I'll take the break.
All right, sounds good. Let's meet up at about 10:01 and we'll get started again. So I'm going to stop recording here.